Hello guys, welcome to Amazing Engineering, and today in this OpenFOAM tutorial we will see how to set a turbulent flow case. Unlike laminar flows, turbulent flows generate the mixing of fluid properties like velocity, pressure gradient and energy, and make the fluid equation more complicated, introducing a new term called Reynolds stress. However, we can simplify the problem using the Navier-Stokes equations averaged by Reynolds and some closing equation models called runs. For example, K omega SST models, K omega model, K epsilon model and realizable K epsilon model. There is no rule that tells us which is the best model to use. In order to know it, we should compare the numerical data with the experimental data, and we have to choose the model which approximates in the best way the experimental data. For our case, we will create this two-dimensional domain, and we have to pay attention to this step, because when a flow reaches a step, there will be the detachment of fluid streamlines, and near the step there will be the formation of a recirculation zone where eddies move in the opposite direction of the fluid. Moreover, if we plot the velocity profile near the step, we can notice the formation of an inflection point which fades as we move away from the step. So let's create our work directory, let's open Salom and let's go to geometry field. In file properties, set meters has length units, and our domain we can set a series of points. So let's go to new entity, basic point. The coordinates of the first point are 0, 0, 0, then 0.435, 0, 0, 0.435, 0.045, 0, minus 0.465, 0.045, 0, minus 0.465, 0, 0, minus 0.365, 0.015, 0, and the last one 0, 0.015, 0. Apply and close. Now let's create some lines to link our points. So select line in new entity. Now let's go to new entity, build face, select the domain, apply and close, and now we have to extrude this face along the direction. So let's go to new entity, generation extrusion, let's call it turbulent case. Select the face, the extrusion vector is the z direction, as the extrusion is 0.5 meter length. Apply and close, and this is our domain. Now let's create the graphs for the boundary condition. So let's go to create graph, select face graph. The first one is called inlet, and we select this face. Outlet, and we select this face. From back, and we select the front and the back face, and walls, and we select these faces. Now let's create the graphs for the mesh. So source face, and we select the back face, destination face, and we select the front face, and the segment graphs called one element edges, and we select this segment. Now let's go to mesh field, select the domain and click on create mesh. We can call it blank case, and we select extrusion 3D. Apply and close. Now we have to create the submeshes. So click on create submesh, select the destination face. We can call it destination, and we select projection 2D. Then one element edges, we can call it one element. We select wide discretization and as hypothesis number of segments. We set only one segment. And source face, we can call it source. We select NetGen 1D, 2D. As hypothesis, NetGen 2D parameters. We set 0 as a minimum size and 0.007 as or 0.07 as maximum size, and we have to create a viscous layer. That's because if we consider a laminar and a turbulent profile, if we want to represent them with the same mesh, we notice that the mesh doesn't get the point near the walls. If we want to get these points, we have to create a viscous sublayer in order to use the so-called wall function, and for the rest of the profile we can use the normal mesh. So the total thickness is for example 0.05 or 0.005. We can set 10 as a number of layers and 1.1 as a stretch factor. Click on OK, apply and close, and compute the mesh. So So the number of volumes is not enough, so let's go to Negent 2D hypothesis and set, for example, 0.005 as maximum size. Clear the mesh data and compute the mesh. We can improve the mesh again, for example 0.001. And the number of volumes now is enough. And as you can see, this is our sublayer. Now let's import the graphs inside the mesh. So click on Create Graphs from Geometry and select Inlet, Outlet, From Back and Walls graph. And now we can export our mesh as a UMV file. And we can save it inside our work directory. Okay, now close Salon. Let's open the work directory. And we have to reach it using bash on Ubuntu application. So change directory mnt c users admin desktop turbulent flow. Now let's create the polymesh directory using ideas unv2foam command, selecting the mesh file. Let's go to polymesh directory, and in boundary field we have to set the type of boundary condition for the graphs. So we can set patch type boundary condition for inlet outlet, empty for back because it is a two-dimensional simulation, and wall for walls graph. Transport properties, we have to set the value of the kinematic viscosity of the fluid. For example, this is the value for water. In turbulent properties, we have to set the runs model we want to use. For example, in our case, we can use k omega SST model. So let's go to zero directory. Let's set boundary condition for velocity file. We can set 0 as start value. The inlet value is 0.135 meter per second. We can set 0 gradient for outlet, empty for from back, and no slip for walls. In pressure file, we can set 0 gradient for inlet, 0 has a fixed value for outlet, empty for from back, and 0 gradient for walls. Omega file represents the frequency of eddies, and we have to set it if we are choosing a k omega model or a k omega SST model. As inlet boundary condition, we have to set the value of mixing length, which represent the distance where a fluid parcel still keeps its characteristic before mixing with the surround fluid. Normally it's equal to 0.07 times the geometrical characteristic of the problem, for example the diameter of a circular pipe, the hydraulic diameter of a square pipe, or something else, and then we set its value. For example, in this case it's equal to 0.00210 meter, and we choose the length of the step as a characteristical dimension, then 0 gradient for outlet, empty for from back, and omega wall function for walls. Note is the eddy kinematic viscosity of the fluid. So we set calculated boundary condition for inlet and outlet, empty for from back, and Knut wall function for walls. K file represents the turbulent kinematic energy of the case, and as inlet boundary condition we have to set the value of turbulent intensity energy of the case. Of course, the bigger it will be, the more turbulent the flow will be. For example, we can set 10% as value of turbulent intensity energy. In outlet we set 0 gradient as boundary condition, empty for from back, and K wall function for walls. And you have to set a boundary condition for epsilon files, which represents the dissipation energy of the case, and they are the same of omega file, except for wall function that is called epsilon wall function. So you have to set this file only if you are using a model based on epsilon property like K epsilon or realizable K epsilon. Now let's go to system and let's set the parameters of the simulation in control dict file. So we use OpenFOAM as solver, we set 0 as start time, 15,000 as end time, and delta t of 0.5, 500 as write interval, and we set only one purge write directory. So let's open bash on Ubuntu application and let's write OpenFOAM. Now that the simulation is finished, we can open paraview with paraview command. Click on apply, select velocity, change color mapping, for example blue to red rainbow, and start the simulation. Now we could plot the velocity profile near the step, so click on plot over line. The coordinates of this point are 0.0300 and 0.03, 0.045, 0. Click on apply. Along each direction select the x component of velocity. Along y direction select arc length, and as you can see, the profile has an inflection point in this part. But if we move away from the step, for example we select 0.15 as point, as you can see, the inflection point is smaller than before. Okay guys, this is all for today. I invite you to subscribe on my channel and see you for the next video.